All right, today we're talking about stereochemistry. And honestly, it's a review. A lot of these graphics were things that I've taken from previous lectures and I've tried to recontextualize. And now that you know these reactions, hopefully the stereochemistry of them makes a little bit more sense. But before we dive fully into the reactions, we have to look back at Vesper. We have to look at how molecules orient themselves in space. So, when when an atom is bound to just two different things or has two number of electron groups is how this thing phrases it. Um, this can be anything like a carbon triple bound to something, or I don't know why I drew that one, or like a carbon triple bound to another carbon and something, or even sometimes a carbon double bound to two different things. You'll see this occasionally, not very much in organic chemistry for undergrads, but this is a thing, right? So anytime an atom is just connected to two things, there's two electron groups, there's no other lone pairs, zero lone pairs. We call that linear. It wants to get these things as far away from each other as possible. So in three-dimensional space, the furthest apart it can get from each other is on a flat page, 180 degrees away from each other. Okay. That changes when you get to three things. When you get to three things, it still stays flat, but the furthest away from each other those three things can get is it kind of looks like a Mercedes-Benz symbol, right? It's all still flat. It's all still on a page. So this would be something like a carbon double bound to something, right? This carbon is what we call trigonal planar. It's flat. It has no need to go in a third dimension because the furthest apart they can get is all on the same plane. So far, almost everything we deal with, number of electron groups is two or three. We're looking at something that's planar. We're looking at something that is flat on a page. We can represent it without a wedge or a dash, no issues whatsoever. But as soon as we get to four electron groups, we start to have to use a third dimension. We start to need to use a third dimension because that's how these things try to orient themselves as far apart from each other in space. So once you get to four, the third dimension is useful. And that's when we start using wedges and dashes. There's another way to think of these number of electron groups when we're talking about carbons in particular. This is an sp hybridized carbon, right? One s, one p. There's two number of electron groups. This is an sp2 hybridized carbon. So one s, two p. That's three electron groups. And that makes this sp3. So anytime, anytime, period, I have an sp3 carbon, any sp3 carbon, any sp3 anything, right? It could have lone pairs. That's going to be in a third dimension. Hopefully this is a better picture. This picture kind of makes more sense, right? Where in order to properly orient any sp3 atom in space, I'm going to have two things that are in plane with the page. One thing that is coming out at me, which is this guy, and one thing that is going back into the page. This is for every single sp3 atom. This is how it is most stable in space. It's got an angle of, each one of these things has an angle of 109.5. It's this kind of famous angle, right? And when you get that angle in four different directions, it has to be in three-dimensional space. So with with sp2, everything is flat. You will never see a double bond, a carbon with a double bond on it, that requires a wedge or a dash. because it's flat. It's trigonal planar. It is literally in the name. It is on the plane. All right. Once it's sp3, it has to have wedges and dashes. So, what is the hybridization of this carbon? I mean, it's an sp3, right? This is an sp2, and this is an sp2. So, these two sp2s are going to be flat. They are trigonal planar. They have no need to go into that third dimension. We can draw them flat on a page of paper. But this sp3 carbon, well, it has wedges and dashes. It has to, because that's how it orients itself in space, right? So if I drew out every hydrogen, technically there'd be one hydrogen on a wedge, one hydrogen on a dash, and one flat hydrogen. The thing is, we just don't do it that much because a lot of times it's irrelevant. So let's look at it. If I swiveled all these hydrogens around and I changed which hydrogen was on a wedge and which hydrogen was on a dash, does that change the picture at all? Has anything changed about what I've drawn? No, these are the same molecules. So oftentimes it's you'll see us draw it if I draw all the hydrogens. Oftentimes we'll just not worry about the wedges and dashes because they're irrelevant. There is symmetry on this carbon. It does not matter which hydrogen is on a wedge or a dash. That information isn't useful to us to determine if it's a different molecule or not. But technically, this is the more correct way of writing it. This is how it's oriented in space. I'll say this is okay. It's okay. Like it works because we haven't lost any important information. I can intuit that one of these is a wedge and one of these is a dash, and it doesn't matter which is which. Let's look at let's look at this next one. Are these two different molecules? No, I mean they're not. They are the same molecule. I'm actually just kind of looking at it from a slightly different angle. But even though I've drawn the wedges and dashes, they're the same molecule. Why?
That's not a chiral center.
This is not a chiral center. There is symmetry here. There's two methyls attached to this carbon. I have two of the same group, right? Just like this picture above with the hydrogens, it does not matter which one is wedge and which one is dash because they're the same thing. It is symmetrical. This is not a chiral center. So in this case, people will often draw it like this, myself included. Does this mean that this carbon is all of a sudden flat? That this sp3 carbon is all on plane? No, it doesn't. This is actually technically the less correct way of drawing it, right? One of these methyls is on a wedge and one of them's on a dash. It's just not important which one's which. So oftentimes people, since I'm not losing information, this is not a real chiral center, I will not draw the wedge or the dash. I think a lot of you guys got so used to relying on me doing that for you that you just assumed that anything with a wedge or a dash is a chiral center. But that's not necessarily true, right? This is not a chiral center, even though I drew out wedges and dashes because there's symmetry through it. But it is true that oftentimes when there is no chiral center, even though it's an sp3 carbon, we won't draw out the wedges and dashes. With a little change, all of a sudden it does matter. Whereas these were the same, now as soon as I make one of these methyls into a chlorine, These are different. Now it fundamentally matters which one is on the wedge and which one is on the dash. Because now this chlorine is bound to a methyl, an ethyl, and a propyl, or a butyl, sorry. So this matters. This matters. It matters what's a wedge and a dash because this is a chiral center. That carbon is bound to four different things. There is no more symmetry. Unlike this hydrogen up here, this carbon with the three hydrogens, where we could just turn it, it doesn't matter. As soon as there's four different things attached to that carbon, it matters. Those are two different things. However, where this kind of gets a little complicated is that you'll still sometimes see people draw this out like this, myself included. You'll see someone draw a chiral center, which is that, without the wedge or the dash. That's communicating something very, very particular. That's communicating that not that it doesn't matter, it's that we don't know. It's a different thing entirely. This is saying that we actually get both of these as a mixture. Both of these are existing at the same time, and we don't actually know the difference. So it's kind of imprecise language. It's best not to use this. And I know there's a lot of organic professors that if you draw this and you mean for it to be racemic or you mean to have both, you'll get credit taken off. It's kind of a lazy way to draw a stereocenter. But what this is communicating is that there is no defined wedge or dashes. Not that there is no wedge or dashes. It's that in my mixture of a bunch of this stuff, I have both of these present. It's not the best way to write it, but people will write it that way. Now, if we remember what racemic means that everything is an enantiomer, which means that every single chiral center are opposite of each other. So in this case, yeah, this chlorine's on the wedge, then the chlorine's on the dash. We've changed from R to S, right? So we flipped the one stereocenter there is, so this is a racemic mixture. But you have to be careful. Racemic is very particular that all of the stereocenters have to be opposite. So if you happen to make a new stereocenter and there is another stereocenter on the molecule, like in this case, this is not racemic anymore. These are not enantiomers of each other. These are diastereomers. Not every. So if you remember, enantiomer means everything is opposite. Where diastereomer is like a disaster. It means that things are different, but they're not necessarily all different, right? So the bromines are the same stereocenter, but the chlorines are on different stereocenters. So this isn't an enantiomer, so it cannot be racemic. This is just a mess. It's a disaster. It's a diastereomer. Okay. So a lot of you guys would just write racemic mindlessly, like, well, I know I get both of the chiral centers, but racemic racemic means something very particular, and it only means something if you have all inverted stereocenters. All right. So what does this mean for reactions? Let's try to do this SN1. So spend a second, do the mechanism. What's happening in this SN1? All right, I kind of helped you out by telling you what it is. But with an SN1, this isn't charged, right? My nucleophile, it's not charged. So it's not a good nucleophile. So my neutral nucleophile is unlikely to react with a neutral electrophile. So I've got to make my electrophile charged. I'm going to do that by getting the leaving group to leave first. This is what makes it an SN1. All right. So is that what you guys got? Well, let's take a second. Let's reevaluate what this carbon actually looks like. So this carbon, well, that was an sp3 carbon. There are four different things attached to it. It lost the iodine and replaced it with nothing. So it's a carbon with three things attached to it and no lone pairs. Do we agree? That's what this carbon now looks like. What would that be on this chart if something had three things attached to it and no lone pairs?
Terminal planner.
It'd be trigonal planar. It has to be. It's no longer sp3. It no longer has four different things attached to it. It lost something and gained nothing in return. It lost an electron group and gained nothing in return. It is trigonal planar. If this carbon is planar, can it have a wedge or dash on it?
No.
No, it can't. There cannot be a wedge or dash on this carbon anymore because it has gone from being sp3 to sp2. It has become planar. So now, when the water comes in, it can come in from one side or it can come from the other. So at this point, since I'm adding into something flat and I'm going from an sp2 carbocation, carbocations are always flat, by the way. They're always sp2, to a sp3, I've now gained that third dimension back. I've now gone back to being three-dimensional. But because it started out flat from this step, where it adds is undefined. It can either add to the front or the back because what it's adding to is flat. Then I'm going to deprotonate it and we're going to get. Can I say this is racemic? There's only one stereocenter and they're
Yes.
opposite. So this is racemic. But you don't just knee jerk say it's racemic. Think about it. I added to something that was flat to make it no longer flat. There was nothing directing the water addition, so it added to both sides. So here's a different dimension picture of it, right? I've got my nucleophile. I've got a flat carbocation, right? It's sp3, or sorry, it's sp2. That nucleophile can add to either side. So anytime you add to something flat, carbocations are included, there's no directional information. Nothing directs the addition. Try this reaction. All right. So I've got an acid. Acids give protons. Acids give protons to things with electrons. Well, this double bond's really the only thing with electrons. So I'm going to add that hydrogen here so I can make the more stable carbocation. All right. So a point to talk about. This carbon went from sp2 to sp2, so it stayed flat. This carbon went from sp2 to sp3. So technically, this hydrogen, I added one hydrogen to the wedge and one hydrogen to the dash. Does it matter to me in this case if I added the hydrogen to the wedge or the dash? No, because this is not a chiral center. There's two hydrogens on it. There's symmetry here. It doesn't matter if I put that hydrogen on a wedge or a dash because it just put the other hydrogen on the opposite. So the stereochemistry does not matter. So I do not draw the stereochemistry here. I do not care about it. But then something interesting happens here. I'm adding something into something flat to make it sp3, right? If I just think about this without thinking about the stereochemistry, this carbon is now sp3. This carbon now goes into the third dimension. I need a wedge or a dash here. Is that carbon a stereocenter? Yes,
No.
it is.
Uh,
How do I know it's a stereocenter? How do I know anything's a
it's
stereocenter?
attached to four different things.
Yeah, this is connected to a methyl, a bromine, an ethyl, and a propyl. Those are four different groups. There's no symmetry there, right? It has to have symmetry. It has to be connected to the same things, not to the same atoms, to the same entire things, right? You wouldn't say identical twins are identical because they have the same pinky nail. You'd say they're identical because their whole being is identical. That means it's important whether or not this bromine is added to a wedge or a dash. And since I added to something flat, Is it going to be on a wedge or a dash?
Both.
It's going to be both. I'm going to get both because I didn't start with any sort of information. There was nothing telling me which side to add to, so I add to both. Again, this would be racemic because it's the only chiral center in there. But it's important to me that you know that not that something's racemic. I could care less if you know something's racemic, really. I care that you know that when this flat thing gets added to, it gets added to either direction. Right? A carbocation is literally an empty space. If you jump into an empty space, it doesn't matter which direction you jump into from. All right. So what do we call? We can do substitutions and never get that carbocation. What do we call that? What is a substitution without the carbocation?
Bad attack.
What? It's it. Well, what's the name of the reaction?
SN2.
It's an SN2. SN2s happen all in one step, right? They happen just like that. We never have to form the carbocation, right? I see a metal, I see sodium. I'm going to immediately draw this out. And look at there. I've got a charged nucleophile. That means that my electrophile doesn't need to be charged to be attacked. So try this SN2 out for size. This is the most straightforward mechanism we have. But because we never went to that flat carbocation, then this is one of the main reasons why it's important that we draw out the carbocation. Because the molecule never went flat, well, this sulfur, this SH could only approach from one direction. There was only one choice, and it was the opposite direction that the bromine was in. This is why we call it a backside attack. It's we never we went from sp3 to sp3, so we kept so we keep the stereochemistry. Well, that's kind of confusing. It's inverted stereochemistry, but you can only get stereochemistry when you have stereochemistry. Does that make sense? As soon as something goes flat, that information is lost. You can no longer direct the next thing. So here's a picture. In comparison to the other one, this nucleophile only has one direction it can come in, and that's opposite the chlorine, the leaving group. Right? We've already shown this before. We've already talked about this before. Try this SN2. Does it matter that I do that wedge? Is this a chiral center? It's not. There's two hydrogens on it. Conceivably, one of them's on a wedge at this point. But this doesn't matter. I can rotate that sulfur any direction and it doesn't change the molecule. That's the same as this, which is the same as having it on a flat. Right? They're all the same because it's just I'm just rotating it and just not drawing the other hydrogens. So this one, it doesn't matter that I inverted the stereochemistry because there's no stereochemistry to invert. This was not a chiral center. Yes, it's sp3. Yes, I did the inversion of stereochemistry, but it does not matter. This is not a stereocenter. Compare that to this. If I tried to rotate this sulfur around so it's flat, I would all of a sudden turn that methyl into a dash, right? That would change the other things on the molecule if I turned that sulfur all around. But down here, it doesn't matter because there's symmetry here. It doesn't matter where the hydrogens are because they're the same things. Okay. So that's why sometimes it matters and sometimes it doesn't, right? They're both sp3, it's both SN2, but one was a stereocenter and one was not. It turns out you need stereochemistry to get stereochemistry. That's the big takeaway. If you have something that has defined stereochemistry, you will get something that has defined stereochemistry out. Try this reaction, but try to be particular about the stereochemistry. So this is one of those weird ones, right? We talked about this the other day. It actually kind of forms this kind of weird three-membered ring. But hold on. We can actually be a little bit more particular about this. What was the Vesper of that carbon? What's its shape?
Trigonal planar.
It's trigonal planar. It's flat. What did it turn into?
Tetrahedral.
It turned into a tetrahedral. Same with this guy. they both turned tetrahedral. So the question is, do we know what side, if this is tetrahedral, it means it has to have a wedge and dash. And to me, these both look like chiral centers. This guy's connected to uh, a methyl, a propyl, and a bromine, and a carbon, and this weird other carbon group. This one's connected to a methyl, a hydrogen, and this weird carbon group, and this bromine. Like these are two chiral centers. It matters here whether or not this bromine was put on a wedge or dash, but since it added to something flat, we actually have no idea. It could have added either direction. So that means this bromine either could have added to the front or this bromine could have added to the back. This is true anytime we add something to a flat structure. You add it to both sides. But this is where it gets kind of interesting. The second step actually resembles something else we've seen. What does that look like?
Backside attack.
It looks like the backside of attack. It looks like an SN2. We're going from sp3 to sp3. So there is defined stereochemistry in the starting material, which means that the product that comes from it will also be, here, let me, this needs focus, will also be defined, right? This wedge bromine stays a wedge because this bond didn't break, but this new bromine attacks on the backside of the wedge, so it becomes dashed. Now try the other one. I'm going to redraw it so it's easier. Again, this bromine adds into the backside. It kicks off this bromine from that carbon. So that means that this bromine stays on a wedge, right? Nothing changed about this wedge bond, right? That's not what I broke at all. And that means this other bromine did a backside attack because that was the only direction it could come in from. So it ends up being on a wedge, which means that the methyl is attached to is on a dash. So since this first step goes from sp2 to sp3, we get both wedge and dash adducts. But since the next step goes from sp3 to sp3, we retain that stereochemistry. Or not retain it, but we keep the fact that there is defined stereochemistry. So this is one of those ones where these are the two products you get, and notice something about the BRs. In both cases, the BRs are what? Well, this BR is on a dash, this BR is on a wedge. So I would say that's anti. They're anti to each other. This BR is on a wedge, this BR is on a dash. That's anti. So that's why when we do this reaction, we say, well, I don't know if it's going to be a wedge or a dash. That first edition of that BR, I'll get one on a wedge, one on a dash. But I can tell you that the information we do have is that they will be opposite of each other when the second one adds in. Because that step, the second edition, is specific. Because going from sp3 to sp3. I'm going from tetrahedral to tetrahedral. I'm not adding anything to something flat after the first step. So this reaction kind of takes everything and puts it together. Add something to a flat thing, I get both wedge and dash. Add something to a non-flat thing, to an sp3 thing, then I get to be specific about the stereochemistry I have. So that's why you'll hear the term anti, right? Whereas, right, I think this is just a good, just it shows everything. Right. So the last stereochemistry thing I will talk about is eliminations actually have a stereochemical component to them. It's kind of niche. You'll see it occasionally, but it's something that's usually taught. I've kind of held off on it because I feel like I want you guys to be really comfortable with eliminations before we get there. But um, do these eliminations. Try these out. All right. So in order to eliminate this leaving group, right? That's a leaving group. I have to take a carbon from next door, or sorry, a hydrogen from next door. So it has to be the dash hydrogen in this case, has to be the wedge hydrogen in this case. So we can push the arrows and do the elimination. All right. I hope none of you guys drew that as a wedge. Why can that not be a wedge? That's sp2. It's planar. So we went from tetrahedral, three-dimensional, to two-dimensional. We went from sp3 to sp2. That means that can no longer be wedged. All right. The second one is similar. It's the same mechanism. Notice on the left side, I'm keeping the stereochemistry because nothing changed about that, right? These weren't affected by this elimination. But this lost its stereochemical information. It went from tetrahedral to flat. So it turns out this top reaction is fast and this bottom reaction is slow. Notice in this top reaction, the hydrogen's on a dash and the leaving group's on a wedge. The bottom, they're both on wedges. With eliminations, things want to be anti to each other. It's actually kind of similar to the inverse of additions. Additions, things tend to like to be anti to each other. Eliminations, they like to be anti to each other. There's better orbital overlap is the reasoning. But this process where the hydrogen is opposite the leaving group, this works a lot faster than this one, where the hydrogen's on the same side. Eliminations also tend to form, oh, this is backwards, sorry. They tend to form trans alkenes as opposed to cis alkenes. They tend to form these as opposed to these. Just because the trans alkenes are a little bit more stable. There's less steric overlap. How come I can always accidentally turn on my eraser, but purposefully turning off the eraser is so much harder? All right, LDA is just a bulky base, so it does an elimination here. The question is, am I going to eliminate this hydrogen or this hydrogen? That's LDA. You can see why it's a good base. You can see why it's bulky. It's literally lithium diisopropyl amide, which is just a negative amine. So is the base going to take the hydrogen on a wedge or the hydrogen on a dash?
The dash.
It's going to take the hydrogen on a dash because it is anti to the triflate. Is that what you guys all got?
Shouldn't the methyl not be a wedge?
Thank you. The methyl should not be a wedge because that's a trigonal planar carbon now. It has become flat. It's no longer sp3. Good catch. I did that on purpose. Again, a strong base. It's not really that important here, but we're going to take this hydrogen. It's not important because that's not actually a stereocenter. But this one was me just showing you that even though it's drawn in a way that suggests that that's going to be my product, it's actually not going to form that. It's going to form this. It's going to prefer the trans to this cis. That's the same thing here. This is just a cis trans question, which honestly is way more common than this. But it is good to know, and honestly good to practice when you draw an elimination to just remind yourself to draw the anti. If you just do it every time you draw elimination, even on this where it doesn't matter, because that's not a stereocenter, there's two hydrogens on it. Um, you'll never forget it. All right. That covers basically all the stereochemistry stuff that we've talked about all class that anybody really cares about. Um, there are other reactions, but they follow the same formula. So like the Br2 reaction also follows the um, the oxymercuration, right? We've talked about how those are similar mechanisms. Um, yeah. So all right, so this is it. This is it for organic one. I'm sorry, we're 3 minutes over. But yeah, today was the last class. I've really appreciated you guys through everything, through what happened last week, and you guys have been nothing but supportive and caring to me, so I really appreciate that. If you could please fill out both the official survey and the one that Canvas sends out. That one actually determines whether or not I get a raise or not, or the magnitude of my raise, or if I can win awards for teaching. So nice words there actually do impact my teaching evaluations and stuff. Uh, but the extra credit survey, I'd really appreciate it if you did that, even if you don't need the extra credit points, just because it helps inform me about kind of how to move my class forward, how to improve at what I do, and also lets me get to know you guys a little bit better. So yeah, I really look forward to reading those. And yeah, if you guys need help for organic 2 and you're not taking organic 2 with me, feel free to always shoot me an email and say, "Hey, I don't really understand this concept. Am I getting this right? Or is this answer correct?" And I can do my best to try to help you out there. But yeah, I think you guys are all going to do great, and hopefully the final's not too bad next week. But yeah, I look forward to seeing a lot of you guys in Orgo 2, and if I don't, good luck. You're going to be great. I believe in you. Hopefully, I've prepared you well enough to take on those courses and be successful in them. Yeah, so I'll talk to you guys later. I'll see you guys around. My office is changing to Carruthers here in the next couple weeks, so I'll be in that building instead of this building. But always feel free to stop by and say hi. My door's open, and if it's not, just knock. I might be there. But yeah, thank you guys for everything, and for the patience for my first semester teaching. I know there were some growing pains, but I really appreciate you guys.